Hi, welcome to another exciting episode of our physics simulation series. I have something exciting to share today. In future, we'll explore some applications of spring simulation such as glow simulation, software simulations, and multi-spring systems. Before moving into those projects, I think it will be helpful if we take a look at the math behind spring simulations. After that, we'll work on various projects, including closed simulations, software simulations, rope simulations, and many more projects. Before we move on to our today's session, let's spare a few minutes and take a look at some of the projects. Here we have a simple spring simulation where each line segment represents a spring. Its behavior is entirely driven by the physics of a spring, which we'll break down in just a moment. Next, we have a closed grid simulation where once again each spring is represented by a line segment connecting points on the grid. We'll cover even more advanced projects in the next episodes of this series, but for now, as promised, let's look into the math behind the spring simulations. Initial equilibrium. Initially, spring begins at its equilibrium position, meaning no external forces are acting upon it. One end of the spring is attached to a fixed support while the other end is free. Applying a force. When a force is applied to the free end of the spring, it begins to deform. Applying a force causes the spring to deform, generating a restoring force that opposes the applied force. The magnitude of the restoring force is directly proportional to the displacement of the spring. This relationship is described by Hooke's law. The spring continues to deform until the restoring force equals the applied external force. At this point, the net force on the spring is zero and deformation stops, removing the force and acceleration. When the external force is removed, the restoring force is still present because the spring is in a deformed state. This restoring force now becomes the net force acting on the spring, causing it to accelerate back towards its equilibrium position. However, the spring's momentum carries it past the equilibrium point, causing it to compress. This compression also generates a restoring force, now exerting itself in the opposite direction. This process of stretching and compressing repeats, resulting in an acceleration motion. Damping. In reality, the accelerations will gradually decrease in amplitude due to damping forces such as friction. With each cycle, the energy of the system is dissipated, reducing the magnitude of the accelerations until the spring eventually comes to rest at its original equilibrium position. Hooke's law. The relationship between the restoring force and the displacement x of the spring is given by Hooke's law. F equals negative k times x, where F is the restoring force, k is the spring constant, a measure of the spring's stiffness, x is the displacement from the equilibrium position. The negative sign indicates that the restoring force acts in the opposite directions to the displacement. Moving on, now let's explore how to represent a spring mathematically and calculate the forces acting on it. A spring can be represented as a line segment with endpoints labeled as P1 and P2, located at coordinates x1, y1 and x2, y2. The initial length of this spring is denoted as capital L. To understand how the spring stretches or compresses, we need to calculate the displacement. We do this by finding the difference in the x and y coordinates of our 2 points. We call these differences delta x and delta y, where delta x is x2 minus x1 and delta y is y2 minus y1. The vector itself can be written as delta x times I hat plus delta y times j hat. We want to know the current length of the spring. We call this m, and it's simply the magnitude or length of the displacement vector b. We can calculate m using the Pythagorean theorem. M equals the square root of the delta x squared plus delta y squared. Next, we need the unit vector b, which we denote as b hat. This tells us the directions of the displacements. B hat is calculated by dividing the vector b by its magnitude m. Now let's talk about the force the spring exerts. This is described by Hooke's law, which states that the force F is proportional to the displacement x. The formula is F equals minus k times x, where k is the spring constant. In this scenario, we assume k equals 1, simplifying the equations to the F equals negative x. The displacement x in our case is the difference between the current length m and the initial length L. X equals m minus L. Substituting this into Hooke's law with k equals 1 gives us F equals L minus m. Now we can find the force vector F. This is the magnitude of the force F multiplied by the unit displacement vector B hat. This gives us the vector equations for F. Breaking this down into components, we have Fx equals L minus m times delta x divided by m, and Fy equals L minus m times delta y divided by m. In real-world scenarios, we also have damping, which opposes the motion of the spring. This is represented by a damping constant. The damped force components are Fx prime, which equals Fx minus the damping constant times the velocity in the x direction bx, and similarly for Fy prime. Finally, let's apply Newton's second law. F equals m times a, where m is mass and a is accelerations. If we assume a mass of 1 and a time safe of 1 for simplicity, then the force is equal to the velocity. This allows us to update the velocities of our points. The velocity of point 2 in the x direction is updated by adding fx prime to the current velocity, similarly for the y direction, and also for the point 1. But with the force subtracted, and finally we update the change in position delta x and delta y by adding the respective velocities. And that is all for the math behind the spring simulations. We have covered how to mathematically represent a spring, calculate the forces acting on it, and update its positions and velocity over time. You'll find the link to the math paper in the description below, so please check it out. This foundational knowledge will help us simulate realistic spring dynamics for various creative projects. In the next part of this series, we'll explore some cool projects based on spring simulations. That wraps up today's session. Thank you for being with me till the end. I will see you in the next video.